Well, suppose I only could afford to have one clerk sitting outside my office, okay, but I want him to be able to respond quickly to a bunch of different questions. Well, suppose he kept a whole stack of papers, not all the papers, they're in the file cabinets, but a small subset of the papers organized. He can store one paper for each first letter of the last name. Right, so when I ask for a bit diddle, he's going to look in his little B slot, which he can do quickly. Right, he just reaches over B slot, looks at it and says, aha, is this page filed under B happen to be bit diddle? So this notion of what we call a direct map cache, where we take some of the information that's coming in, we take the address, that in this case the name, and we have a mapping function that tells us which, and we have a small array in our, we're going to look in our cache, and each of the incoming addresses will be found in a specific slot in the array. And which slot it is depends on how I map the addresses to the slot number. But once I've done that mapping, I will look in that slot and happen to see if I have that address. Right, so I'm coming up with sort of a way in which I can sort of organize my cache memory. It's going to be relatively inexpensive because I'm only going to be doing one comparison. And I'm going to be using some information from the incoming address to pick which one of the small number of slots to look at. Okay, now the problem with this scheme is that depending on how I map the incoming address into the slot, I may potentially have a lot of requests, all of which map to the same slot, and then my cache isn't doing me any good. I keep asking for Bs, and there's only one B slot. Right? So I have to be a little careful in choosing how I map the incoming address to slots to make sure that most of the addresses that are coming in sequentially, using, and remember there's sort of a pattern to these addresses that are coming in. Okay, I want to look at that pattern, understand what that pattern is, and try to figure out a mapping function so that most of those addresses will map to different slots. And then I can get away with a single comparison. Okay, and in this particular case, if I sort of organize by last letter, okay, in this sort of trivial thought experiment, you can see I do better because they're mapping to different slots. So, and it doesn't eliminate contention, but we hope that statistically we might be able to do well if our mapping function is likely to map elements of our working set to different locations in the cache. That's really what we want to do. These are the locations we're trying to access, this set of locations. Okay. If I can get them to all live in different locations in the cache, hopefully without having to buy a fully associative cache to do it, I should be in good shape. And it turns out, and this is where we're going to spend some time getting to, it turns out we can come up with a hardware architecture that does this. So here's sort of the circuit diagram for a direct map cache. We're actually going to use one of these small fast memories, okay, a memory system that has, at most a few thousand locations. So to make it fast, we're going to use the low order bits of the address as an index to pick the slot we're going to look in, and then we're going to compare the high order bits of the incoming address with the tag field to see if we have that information. So any particular address, any particular combination of bits, will, if it lives in the cache, will live in a very particular line of the cache. Okay, and that line is determined by the low order bits of the address. And then to check to see if that line is holding the information we want, we compare the higher order bits of the address, the ones that weren't part of the index into our cache memory. So these high order T bits, we compare them against the tag field in memory. So this, as I say, this memory here is built out of these small but fast caches. The little top-level caches that you have, the level 1 caches you have, are probably only a few thousand entries long. Okay? But they're very quick. They respond in tens of picoseconds. So, and there's a single comparator associated with each one of these pieces of cache. So that's a direct map cache. We haven't completely solved the contention problem. The idea of using the low order address bits is good because in theory if we're doing mostly sequential accesses, because we're stepping through a program or something like that, the low order bits or the higher order bits stay the same as the low order bits that are busily incrementing, right? As you go 0, 4, 8, C, all those zeros at the top still stay 0 as the low order bits that are changing as I walk through the different addresses of a program. And occasionally I go back to the beginning of the loop. If I can arrange for all the instructions in the loop to map to different cache lines, then I will find all the locations of my loop in the cache. And this particular, using the low order address bits, okay, is as the index here, is my key for mapping the address to my limited number of cache slots in a way that I expect that to win most of the time. Everybody sort of see the reasoning there, why I'm expecting this to work okay? Okay, now we always have contention. In other words, it is possible if I do a data access or I jump to a different part of my memory that I'm going to produce some low order bits that overlap the ones that corresponded to the program I was running, and now the information won't be in the cache. So I do have this contention problem. There will be some misses, and our goal for next time, okay, next Tuesday, is to see here my direct map cache was attractive because it was inexpensive but suffered from a collision problem. This cache can always store any set of n addresses. Okay, there's no notion of a collision because any address can live anywhere in the cache. I don't have the problem of two different addresses mapping to the same cache location, and then I can only be storing one of them, so the other one's a miss. The fully associative cache is very attractive from a notion of collisions because it doesn't have any, okay, but is very expensive in hardware. So our next step is to see, is there a happy middle ground? And there must be, because your machines work pretty well.